Fractals and patterns are everywhere and very evident in nature. It is very fascinating to dig deeper into this mathematical concept because of how amazing the numbers and concepts are. You may think that the world is created by divine being because of frequent presence of this concept in nature, especially in art and architecture. So today, I'm going to talk about fractals and patterns, including its evidence, examples, and applications in nature, technology, and art. For this topic, we're going to focus on discussion of the Fibonacci sequence, the golden ratio, and fractals. First is the Fibonacci sequence. First, we look into the history of Fibonacci sequence. Who introduced it? Fibonacci sequence was named after Leonardo of Pisa, also known as Fibonacci, who first observed the pattern while investigating how fast rabbits could breed under ideal circumstances. Introduced it in his 1202 book, Liber Abaci, where he introduced the sequence to Western European mathematics. Start with the male and the female rabbit. After a month, they mature and produce a litter with another male and female rabbit. A month later, those rabbits reproduce, and out comes another male and female, who also can mate after a month. After a year, how many rabbits would you have? The answer turns out is 144, and the formula used to get to that answer is what's now known as the Fibonacci sequence, according to Gosset 2018. And this is the observance of Leonardo of Pisa on the breed of rabbit, although the pattern was already discovered by Indian mathematics. Now, by definition, Fibonacci sequence where first two numbers are 1, each subsequent number is the sum of the previous two. In mathematics, the sequence is defined by the formula f sub n is equals to f n sub n minus 1 plus f sub n minus 2. Now, when you compute the numbers starting 0 and 1, 1 and 1, you can compute for the Fibonacci numbers. First, 0 plus 1 is equals to 1. Then 1 plus 1 is equals to 2. Then 1 plus 2 is equals to 3. And 2 plus 3 is equals to 5. If you continue computing using the formula, you will get the Fibonacci numbers, which are 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. Now, these numbers are used in art and architecture with the basis of the golden triangle and Fibonacci spiral. As you can see, if you draw a triangle by using the base proportion 1.1 is to 1.61803 ratio, these spirals are equivalent in nature, such as heart of sunflower, snake shells, and in some plants. Now, you can get these rectangles which are based on Fibonacci. Now, using these triangle formations, we can form a spiral that follows the 1 is 1.61803 ratio. These spirals are evident in nature, such as heart of sunflower, stick shells, and in some plants. Now, let's look into some examples where the Fibonacci sequence are visible in art, nature, and technology. Here are examples of sequence present in nature. One of the most common are the flowers. Examples are buttercups, which has 5 petals, delphinum with 8 petals, marigolds with 5 petals, and iris with 3 petals. If you observe the number of petals in a flower, you'll realize that these petals count are Fibonacci numbers, which are 1, 1, 2, 3, 5, 8, 13, 21, and so on. Fascinating, right? Now, Let's look into evidence on Fibonacci sequence in art. First is the girl with the pearl earring. As you observe, the painting was designed by following the golden rectangle or the Fibonacci spiral. Also, if you measure the distances in the painting and find its ratio, you observe that the ratio follows the ratio of consecutive Fibonacci numbers. The same applications with the Athens in Greece. As you can see, the architecture of the infrastructure was constructed in a way that also follows the golden rectangles. Well, if you want to try to measure the actual dimensions of the Athens, you'll realize that it is constructed in a Fibonacci sequence pattern. Another is applications of fractals in technology. One example is dynamic programming. Let's define what is dynamic programming. Dynamic programming is a method for solving a complex problem by breaking it down into a collection of simpler subproblems, solving each of those subproblems just once, and storing their solutions, ideally using a memory-based data structure. And basically, Fibonacci sequences are used to solve problems by recursion and memoization, wherein methods in solving the Fibonacci numbers are recording to solve bigger numbers in an efficient manner. This can be used to improve and fast-track programming in computers, wherein big problems are solved faster by using subproblems which are solved already, rather than repeating computation over and over again. Now, Fibonacci sequences in dynamic programming have important uses in computers such as the following. Computer algorithms. Dynamic programming is a technique in computer programming that helps to efficiently solve a class of problems that have overlapping subproblems and optimal substructure property. Such problems involve repeatedly calculating the value of the same subproblems to find the optimal solution. Next, optimization and programming. Optimization are one of the most important applications of this concept. In computer science, optimization is when the underlying code of a software system is altered so that the program runs more efficiently. For example, a computer program may be optimized so that it uses less memory, draws less power, or accomplishes the same result using fewer operations. Lastly, improving efficiency on computers by avoiding repeated work by remembering partial results. Now, Fibonacci sequence is connected to the ratio 1 is to 1.61803. The ratio is called the golden ratio. If you divide if you divide consecutive Fibonacci numbers, you can observe that as the numbers are getting higher, it is approaching the golden ratio. Let's try to divide two consecutive Fibonacci numbers. 1 over 1 is equals to 1. 2 divided by 1 is equals to 2. 3 divided by 2 is equals to 1.5. 5 over 3 is equals to 1.667. And 8 divided by 5 is equals to 1.6. 13 divided by 8 is equals to 1.625. And 21 over 13 is equals to 1.61538. And if you go further dividing large numbers like this, for example, 377 and 223, if you divide it, it's very close to the golden ratio already, which is 1.61803. So, golden ratio symbolizes the phi, which is the golden mean, which is equals to 1.61803398875, which are present in nature and architectures, just like the examples mentioned in the Fibonacci sequence. By definition, the golden ratio is the same as the ratio of their sum to the larger of two quantities. Mathematical definition: A plus B over A is equals to A over B, where A is greater than B and B is greater than 0. Now, let's see Now let's see some examples of the golden ratio in art. Leonardo da Vinci in his artworks, it can be observed that he uses the golden rectangle pattern in creating his artworks. First, Mona Lisa, where, where when the dimensions are measured, you'll get the golden ratio value. Next is the Vitruvian Man. Here, Da Vinci presented a golden ratio that is also applied in human body. If you measure your body, like toes to navel and toes to hips or shoulders to middle of your hand, and if you divide those two numbers, you get the golden ratio value. Another example is golden ratio in architecture. As you can see, the design in the Cathedral Notre Dame de Paris follows the golden rectangle pattern. If you measure the dimensions of the establishment and divide two consecutive numbers, you'll see that it follows the golden ratio. Same with Taj Mahal, a famous heritage in India. Now, let's have a sample problem on the Fibonacci sequence and the golden ratio. Layers of a pyramid was constructed in a sequence that follows the Fibonacci sequence. The first layer contains 2 blocks and the sixth layer contains 8 blocks. How many blocks does the 23rd layer contains? Yeah. Using the formula, the recursive formula, f sub n is equals to the quantity of 1 plus the square root of 5 raised to n minus the quantity of 1 minus square root of 5 raised to n all over 2 raised to n times the quantity of square root of 5. Now, using the formula and by substituting n with 23, because the missing is the 23rd term, so thus n is equals to 23, the answer would be 28,567, which is the 23rd term in the Fibonacci sequence. Now, let's try to solve the problem with another solution using the golden ratio. First, let's use the same problem. Now, the given is n is equals to 3 and a is equals to 8, which is the 6th term, which is equals to 8. And f sub n is equals to, this is the formula, f sub n is equals to f sub a times the golden ratio raised to n minus a. Now, let's find f sub 3, which is equals to n. F sub a, which is the 6th term, is equals to 8, and n minus a is equals to 17. Now, let's substitute all values. Using calculator, and rounding off the value, you'll get 28,567, which is the 23rd term in the Fibonacci sequence. That's it. You can try creating your own problems or find questions online that you can solve regarding this topic. Now, let's move on to the last topic, fractals. By definition, fractals are operations of shrinking and moving that are applied many times, results of repeatedly performing the operation of shrinking and moving. It results through following a simple process that goes through infinitely many iterations, thus becoming a very complex process. A fractal is a never-ending pattern. Fractals are infinitely complex patterns that are self-similar across different scales. They are created by repeating a simple process over and over like in a time loop. Also, we can see fractals everywhere as the nature is full of fractals. Fractals involve symmetry of magnification called dilation. Now, with some brief history, fractals are coined in 1980 by Belgian mathematician Benoit Mandelbrot, and fractals are named as fractals because it reminds him of the word fraction. Now, since fractals are a complex process, it is certain that there are qualifications of these patterns for an object. Lines or patterns are said to be fractals. These qualifications are called fractal properties. What are these fractal properties? First is self-similarity. Many fractals possess the property of self-similarity, at least approximately, if not exactly. A self-similar object is one whose component parts resemble the whole. This reiteration of details or patterns occurs at progressively smaller scales and can, in the case of purely abstract entities, continue indefinitely, so that each part of each part, when magnified, will look basically like a fixed part of the whole object, and that is according to Britannica. In effect, a self-similar object remains invariant under changes of scale, and it has a scaling symmetry. To illustrate, here for example is the Sierpinski triangle. We can see that the triangle contains three symmetric and repeating patterns. Let's encircle it. Now, these patterns are self-similar. Next property is the fractal dimension. Geometry deals with objects with integer dimension. Here in this property, shapes can be reduced in size with the same dimension repeatedly, smaller and smaller. Here, reduction in size of shape is possible, wherein reduced shape numbers are proportionally the same. Also, the original shape can be divided into little pieces of the same reduction size, but the dimension of the original single shape is retained. For example, this cube. Its size can be reduced to 1/2, resulting in 8 number of cubes. The same reduction can be repeated until cube numbers are getting bigger and each cube size getting smaller. And in this repeating sequence, the dimension of the original cube is still the same. Last is iterative formation. Fractals are formed by iterative process, where a shape are infinitely repeated or base shape are iterated to transform it into fractals. These properties are seen in the constructions of fractals like the Sierpinski triangle, Koch snowflake, Julia sets, Cantor sets, and more. Now this iterative formation used in fractal construction can be applied in technologies. Now, this iterative formation used in fractal construction can be applied in technologies. For this, we'll discuss Mandelbrot set, which are seen in computer graphics, and Koch snowflake, which are used in designing fractal antennas. First is the Mandelbrot set, which are applied in computer graphics. So what is Mandelbrot set? Mandelbrot set is defined to be set of points on a complex plane where the algorithm are computer based on the recursive formula, which is z sub n is equals to the square of z sub n minus 1 plus c, wherein c represents complex number and z are real numbers. Mandelbrot set are created only when personal computer was invented, because a human cannot infinitely solve the set of points to create the Mandelbrot set. With the use of computer, it automatically computes the recursive formula multiple times to plot the dots infinitely that would later form the famous Mandelbrot graphics. Now, let's try to understand the formula. Complex numbers. C, which are complex numbers, which is defined to be combination of real numbers and imaginary numbers. What is an imaginary number? So for example, square root of 1 is equals to 1, but the square root of negative 1 is not a perfect square, and negative square roots become positive square roots. Although mathematicians identified a certain value to square root of negatives values, which I, and I means imaginary number. Basically, Mandelbrot set are plotted in a graph. So, where can we find these imaginary numbers is in the Cartesian plane. I, as defined, which are imaginary numbers, are axes perpendicular to the number line, which means that imaginary numbers are number I times the real numbers perpendicular to the axis. For example, in the y-axis, 3i number line is perpendicular perpendicular to the real number 3 in the axis, another real number -1 in the x-axis, and the imaginary number in the y-axis 3i. The point where the two numbers would meet would form a complex number which is -1 plus 3i. By plotting all the complex number in the graph, Mandelbrot set can be formed. Although not all complex numbers are included in the Mandelbrot set, so how to determine if a number is included in the set? Here is the condition. If the number value does not grow to infinity or somewhat stays or becomes smaller or not grow without band. In computing, we'll use the formula of the algorithm. Computation always starts with z is equals to 0. Let's try to find 1 and -1 if these numbers are included or not in the set. Let's use the recursive formula and let's set the complex number 1 as 0i, which is the complex number when the real number is 1. Now z is equals to 0. Let's substitute. F of z is equals to the square of 0 plus 1, which is equals to 1. And now this 1 is equals to z, which will be used to substitute the z in solving the equation. Now, f of 1 is equals to the square of 1 plus 1, which is equals to 2. And f of 2 is equals to the square of 2 plus 1 is equals to, and this is equals to 5. And f sub 3, which is equals to the square of 3 plus 1, which is equals to 26. Now notice that it is growing bigger and bigger. Thus, 1 is not part of Mandelbrot set. Now, let's try the real number 1 and we can set the complex number -1 plus 0i. Using the same method, f of z is equals to the square of 0 plus -1, which is equals to 1. Now, we'll use the z as -1. Now, f of -1 is equals to the square of -1 plus -1, which is equals to 0. Now, when you substitute the 0, you'll get -1 and vice versa. Notice that it stays somehow and it does not grow without bond. Hence, it is included in the set. Now, plot all complex numbers included in the set by using the formula and computing multiple times, which can be done by computers, and you will form the Mandelbrot set. Now, fractal geometry also has contributed to form computer graphics like this. Fractal algorithms have made it possible to generate lifelike images of complicated, highly irregular natural objects such as the rugged terrains of mountains and the intricate branch systems of trees, and this Mandelbrot set. Now, next is the Koch flake applied in designing fractal antennas. First, what is fractal antennas? What can it do to improve technologies? So, fractal antennas is specifically use triangles to form the Koch snowflake to maximize the length or increase the perimeter on inside sections or the structure of material that can receive or transmit electromagnetic radiation with a given total surface area or volume. It is very compact, multiband, wideband, and it is used in cellular telephone and microwave communications. It is also capable of operating efficient performance at many different frequencies simultaneously. Obtain radiation patterns in input impedances similar to longer antennas, keeping the size of antenna really small, also one of the benefits of fractal antennas. And fractal antennas are much more efficient antennas than traditional ones. It is smaller in size. Now, fractal antennas are constructed using Koch snowflakes. So let's look into the construction of the Koch snowflake. Here, we are going to follow steps on fractal constructions. Step 1. Draw a triangle and set the motif. And this is the motif. Here, you substitute each segment of the triangle with the motif. In step 2, replace each side of the triangle with the motif. And you will form this. And in step 3, repeat the process of replacing each segment with the motif. And you will form the Koch snowflake. And that's it. Thank you, and I hope you learned something. Let me finish this with my own quote. Fractals and patterns are everywhere in nature. Why not use it to innovate? Thank you. This is Keith Paule from the LSU Mechanical Engineering.